video is over periodic trends, and what you need to be able to do here by the end of this video, be able to compare different properties of each element with another element on the periodic table. So the first property we're going to talk about is the atomic radius. And it's a little bit different definition of radius than you would have gotten in math class. It's the distance measured between the center of two adjacent atoms. So if you take a look at this picture here that just popped up, here's one atom, we'll call it carbon, doesn't matter what atom it is. Here's another atom, same atom, here's their nuclei. You measure the distance between the two nuclei, and then you halved it. And that part right here is going to be considered your atomic radius. So what's the trend? How do you know which element is larger or smaller than another element? Well, the first thing you can do is memorize this chart. But I would recommend it. If you look at the trend, it's really big down here in the bottom. And it's really small up here at the top. It's really big on the left and really small on the right. And that's the trend I want you to know. You can look at it just like that. So for comparing fluorine up here in the top right, and we'll compare francium down here in the bottom left. Fluorine is going to be substantially smaller than francium because fluorine contains less protons, less neutrons, less electrons. Francium has a whole bunch of protons and neutrons and a whole bunch of electrons. So what we're going to do is we're going to draw this arrow from fluorine down to francium that shows it increasing as we go down and to the left. Or we can say it decreases across the period and increases as you go down a group. So that's the trend. So you can compare any one of these. Whatever this is going to be a lot smaller than whatever this is. Whatever this is going to be a lot smaller than whatever this is. And that's how this becomes beneficial. So ionization energy, what is it? You can read this. The amount of energy required to remove one outermost valence electron. So what we're actually doing, you can see over here, if we remove electrons, we're forming a positive ion. So you can rephrase this as formation of a positive ion. Here's the trend. The first thing you need to recognize when dealing with ionization energy is the higher the energy, the harder it is to remove that electron. The reason is, the more electrons you get on the outside, the closer you become to 8, the more you want to be 8. If you take a group 1 element like lithium over here on the left, it's a group 1 element, so you know it only has 1 valence electron. It wants to have 8 valence electrons. So what it can do is get rid of one of its valence electrons and just go back to a different subshell. So it easily gives up its 1 electron. Then you have fluorine. It's got 7. It's a group 17 element. It's got 7 valence electrons. It really badly wants to become 8. So fluorine is not going to want to give up any of its electrons because it's almost to where it wants to be. So fluorine is our highest energy electron. Okay, now what's about the difference between this lithium atom and francium? Well, as you go down a group, you add a whole bunch more electrons. But as you add more and more electrons, the electrons become farther and farther away from the nucleus, so they're not held on as tightly. So the trend I want you to get is it's very, very weak down here in the bottom left. And it increases as you come to fluorine. Remember, the higher the ionization energy, the harder it is to move that electron. And there's your definitions right there, your little explanation. Now, electronegativity, very similar to ionization energy, but it's the attraction of an atom, whereas ionization is the removal of an electron. Electronegativity is going to be the attraction of one. It's the ability to gain another electron. And this has almost the same explanation as ionization energy did. Because it's pretty much the same thing. Now, fluorine, it had high ionization energy because it did not want to give up any of its electrons because it was almost at 8. Now we're talking about gaining electrons. So the higher the electronegativity, the more likely it is to gain an electron. So fluorine's at 7, because it's a group 17 element. It's got 7 electrons. It wants to get to that 8. So we say fluorine has our greatest electronegativity because it's going to suck up that 1 electron. If fluorine's ever in a battle for electrons, fluorine's going to win. Okay, let me come back over here. Lithium's not very likely to get that electron. Because if you think back to the last definition, lithium only has 1 valence electron. It's more likely to give up an electron than it is to gain one, so it's not very high. And we can come back down here to francium again. And the valence electrons, once again, are getting farther and further from the nucleus. So as they get further away, they don't react as much. So you have the same trend. It starts small down here at francium and increases up and to the right as you go to fluorine. Okay, ionic radius. this is how big the ion is compared to the neutral atom. This can get kind of weird. What I want you to get from this is the ions form have different sizes than the neutral form. We'll talk about the trend, but it can get kind of complicated. What I really want you to know is that the ionic radius, the trend is it decreases as you go down a group. You can't really go across a period because you're going between metals and nonmetals, and it's going to go up and down. But the other trend I want you to know, if you take a look at this graph over here, you have a positive sodium ion. So sodium ion, so this is sodium with a positive ion. You can see that that radius is slightly smaller because sodium just lost this electron. So we can mark that out. And now, since that electron is gone, you have the same amount of positive charge coming from that proton. So that same amount of positive charge is now distributed over fewer electrons, which means every electron is going to get a stronger pull from the positive charge, and that positive ion is going to become smaller. Now, if we take that same neutral sodium atom and we want to make it a negative ion, if we want to form something like sodium negatively charged, you're going to have to add another proton. And you can't just add it right next to it. What's going to happen is you're going to add it to the same orbital, but to the opposite side. Because these electrons are negatively charged, they're going to repel each other. And then if you think about why the sodium positive cation became smaller, the opposite is true for the negative anion becoming bigger. Because you added another electric charge, the positive and negative attraction is now spread out over more electrons, so it's going to relax and become a little bit bigger. So, all you need to do now, complete this section labeled as practice, and you're going to have questions, but you're going to get a lot of work on this in class, so don't freak out if you're not quite getting it immediately.
We've covered a lot of ground, shared a few laughs.